we can next look at another property of solutions, which is that their boiling point and freezing point will change depending on the amount of solute that we're adding. One important effect of this, or rather something we do as a result of this, is in California we don't typically have snow, but perhaps you've seen in movies, or some of you who live not in Ridgecrest who have snow, probably know that they salt the roads during winter time. And the reason for that is by adding a solute, we're actually going to lower the freezing point of our solution. And so it's going to help to melt the ice or snow by making it actually freeze at a lower temperature than it normally would. And so at 0 degrees Celsius, pure water freezes. But salt water would freeze at a much lower temperature. Or perhaps you've considered something like vodka. Vodka, you may know, if you put it in the freezer, it's 40% ethanol by volume, 60% water. It doesn't freeze at negative 22, or negative 20 is about where your freezer is, negative 20 degrees Celsius. So there are definitely ramifications. And you probably know that the boiling point will increase as well, if you salt the water. Salted water boils at a higher temperature than pure water does. And so boiling points with solutes go up, and freezing points go down. And both of these are related to each other. We just discussed how the vapor pressure changed when we added a solute, right? We're adding new intermolecular forces in. And so more IMFs, more intermolecular forces, means more energy to get free of those, to break all of those intermolecular forces, so your boiling point goes up. Your freezing point goes down for the same reason. There are more IMFs, so it's harder for molecules to organize themselves. So consider you have solute particles that are kind of in the way of molecules organizing. So remember that solids organizing, yeah, that looks like it's correctly spelled. Solids are nicely organized typically, right? We have things fixed in position and they're all connected to each other. For example, with water, when it turns into ice, you have these lovely hexagonal crystals forming with water molecules hydrogen bonding in place. If you're throwing a solute in the way, those water molecules can no longer organize as effectively. And as a result, you need to take away more of their energy in order to get them to freeze. And so we're going to see that both of these we can relate to a couple of constants. We're going to see that the change in either boiling point or freezing point, or we might say melting point, remember these are all the same terms, that this would be related to, for example, if we look at boiling, we're going to have a constant, which we'll talk about. We'll have our Van't Hoff factor from before. Remember, that's the number of particles a particular solute dissociates into, multiplied by the molality of the solvent. This is the molality. I'm sorry, of the solution, not the solvent, of course. I is your Van't Hoff factor. And then this Kf is called, Kb. We're doing boiling right now, not freezing. We're going to see it's the same equation for freezing. This would be what's called the Cryoscopic Constant. You don't need to know that name, don't worry. Or we might call it the boiling point elevation constant. And this is just a number. It varies by solvent. For example, Kb for water is 0.512 degrees Celsius per molal. And for something like, I have a list here, how about ethanol? For ethanol, it's 1.22 degrees Celsius per molal. These are just, you don't need to memorize these, of course, but these are just some examples of the constants we're looking at. And so it's simply a matter of understanding that as your concentration goes up, your molality goes up, your change in boiling point or freezing point will also change proportionally. And we see that we have the Van 't Hoff factor in effect here. Remember that Van 't Hoff factor is different for ionic compounds versus covalent compounds in water. Let's take a look at an example and see if we can't figure out what the boiling point change will be. If, let's say, we're going to put 10 grams of benzene is dissolved in, we'll make this nice, how about 125 grams of carbon tetrachloride. What is the boiling point of the solution, given the following information? We have to understand that we have a our pure boiling point. Our pure boiling point of carbon tetrachloride is 76.8 degrees Celsius. And Kb for this is 5.02 degrees Celsius per molal. Remember that the change in boiling point, it's always kind of our final minus our initial. And understand that our initial one in this case is the pure solvent. So that's our pure solvent there. And so we can apply these figures to our calculation. Remember our formula here, delta Tb, the change in boiling point, is equal to Kb times I times the molality of the solution. Kb is given to us in the problem, 5.02. I is going to be 1, because this is a covalent molecule. We also have a nonpolar solvent, so for both reasons, I is 1. And then we just need to calculate the molality of the solvent. Of the solution. So, Kb, 5.02 degrees Celsius per molal, 1 for our Van 't Hoff factor. And then the molality is going to be the moles of solute over the kilograms of solvent. Remember that molality is the only one that has solvent as part of its formula. So we can put that at the bottom. As for the moles of solute, we're going to have to do a quick calculation. Let's just do that right here. 10 grams. It's actually one I don't have memorized, so let's go ahead and do it. So 12.01 times 6, that's carbon, plus 6 times 1.008, that's hydrogen. We're looking at 78.108 as its molar mass. And so 10 divided by that number is 0.12802, 3 sig figs. So we can go ahead and plug this in, 0.128. We'll just leave that as that, it's close enough. And so, once we plug in these numbers, we're going to get the change in boiling point. And we're going to have to move that down here. So our change in boiling point is going to be all of this put together. So 5.02 times 1 times 0.128 over 0.125. Divide by 5.02. And we get 5.14. Notice that for the units here, molal, although I have not necessarily, I put moles over kilograms here, this unit here would be molal. Remember, molal is moles per kilogram. So those two units will cancel out. Van 't Hoff factor doesn't have a unit, so we end up with degrees Celsius. This is what we showed, right? We're looking at a change in temperature. And so if we want to find out the new temperature of our solution, the new boiling point, remember that our new boiling point minus our original one is going to be equal to that 5.14. And so if we have our initial boiling point, go ahead and look back up, that was 78 or 76.8 degrees Celsius. If we go ahead and solve this, we're going to get 81.9 degrees Celsius with applicable sig figs, right? So with this, we see that our boiling point has increased. That's always something we should see when we're looking at boiling point elevation. We're going to see for freezing point, the formula is exactly the same, except we're going to have to throw in a negative into the formula. So for freezing, the formula is the same. So instead of looking at boiling point, we're looking at freezing point. We're looking at now Kf. We can actually put our negative value in here right before the Kf times I times the molality of the solution. So it's exactly the same, except it's negative. And just be aware, Kf is a different constant. It's called the cryoscopic constant. Cryoscopic. And again, you will always be provided this, or you're calculating it yourself. For example, we have a couple. For water, it's 1.86 degrees Celsius per molal. For carbon tetrachloride, it's 29.8. Wow, quite a huge difference there. So just a constant. Just be aware these have the same units. Everything else is going to be the same. The only difference here is this negative. And I'm going to make that, in fact, a different color, just so we are fully aware that it is present. Because the freezing point should always go down. So we have to make sure that we have a negative in here to indicate that our change in temperature is a decrease. Temperature should always go down when freezing and always go up when boiling. And so you'll have plenty of practice on working through this sort of problem.